Hello, I am Kevin Litwin, and I am here today to talk to you about the baeyeroxidation. As we can see from the overview, there are three main things that we are going to use in this oxidation. One of them is an aldehyde or ketone, which can be seen here. A peroxide, which can be seen here, and an example of this is hydrogen peroxide. You all know that. A hydrogen peroxide, or a peroxide, is characterized by this oxygen-oxygen bond right here. Two oxygens bonded directly to each other. And the last ingredient in our reaction is a Lewis acid. This is commonly seen as H+ and BF3. The Baeyer oxidation is commonly done in the solvent CH2Cl2 dichloromethane. Now what this reaction does is it takes an aldehyde or ketone and on an alpha carbon installs an oxygen and turns a ketone or an aldehyde into an ester. Now if we come over to the product board, we can see that if we start with a ketone, we'll get an ester. If we start with a cyclic ketone, you'll get a lactone. And if we start with an aldehyde, we get a carboxylic acid. Now I have examples of all of these here. A ketone, this, has two alpha carbons. Now this reaction differentiates between this alpha carbon and this alpha carbon. The differentiating point is the carbon that can best accept a positive charge through the mechanism, which James will shortly show you. So, if we're going to install an oxygen atom here between this carbon and this carbon, our product will be as follows. Now, we can see that the oxygen has added in between this carbon and this carbon. Same thing happens for a cyclic ketone. The carbon will differentiate between this carbon and this alpha carbon because this carbon is better at sustaining a positive charge. So the product we get here is as follows. And this is called a lactone, which is a... Now we can see if we start with an aldehyde, we get a carboxylic acid. This transformation will add a oxygen here to give our carboxylic acid because the hydrogen is the best group at accepting positive charge. So our product would be as follows.
Go.
And now James will explore the mechanism and show you an example which utilizes this ketone and makes this ester.
Go.
Hi, I'm James Anand, and I'm here to explain to you the mechanism of how exactly it is that the Baeyer-Villiger reaction works. So the reaction that we're going to be doing today is we're going to be taking this asymmetric ketone, and we're going to be using, for our peroxide, MCPBA, metachloroperoxybenzoic acid, and we're going to be using hydrogen ions as our Lewis acid. And it will make this ester. And so this starts very similarly to much of the aldehyde and ketone chemistry that you learned in Organic 2. The ketone is activated by adding the acid to the oxygen, which creates this. This especially activates this carbon, makes it especially electrophilic, as can be seen by its resonance structure. Here. So what's going to happen is this oxygen is going to attack the electrophilic carbon, and it's going to leave us with this complex. This is the MCPBA, the peroxybenzoic acid. And then from here, the positively formally charged oxygen will regain its neutrality by kicking off that hydrogen and leaving you with this species here. And this is where everything kind of gets interesting. The ketone reforms, the carbonyl group reforms, and as that happens, these electrons in between this carbon and that carbon add to the oxygen. And as those electrons add to the oxygen, these electrons get dumped on that oxygen, which leaves us with this molecule and this molecule, which is resonance stabilized. The H plus comes off, which leaves us with the ester that we originally looked for. And that'll work for aldehydes and cyclic ketones, all sorts of things.
Cool. So you may be wondering how this reaction is useful. This reaction is complex. It takes a simple molecule, such as a carbonyl group, and turns it into a much more complex molecule like an ester. And this is exactly what it does. It adds complexity to your molecule of choice. It works on non-terminal functional groups. Now over here we can see this is the way that we learned prior to make an ester. We take a primary alcohol, turn it into a carboxylic acid in this example. But what we ideally do is use a primary functional group and use Fischer esterification to make an ester. Using the Baeyer oxidation, we can take a secondary alcohol, make a ketone, and then make an ester out of this. This is very important because we can use a much more varied reagents list to make an ester. This also reduces waste. In some of the mechanisms that we know how to perform this reaction, we can use hydrogen peroxide. This is a not toxic material and produces minimal waste. Now I know I've said complexity and low complexity. This reaction is very easy to perform in the lab. It has low complexity methods and there are not very large amounts of knowledge you need to gain in order to produce an ester using this synthesis. And lastly, it's inexpensive. The reagents used in the baeyeroxidation are very cheap and commonly used in the laboratory.